So we are going to consider this question on
Reversible isobaric process.
the question says a certain mass of gas expanding reversibly at constant pressure does 5 kilojoules of work. Calculate the quantity of heat which is transmitted to the gas and how much of this heat is used to raise the internal energy of the gas. Assume only that the gas is perfect and that the ratio of specific heat at constant pressure and volume is 1.66. So first, let's pick out our parameters or everything that was given to us in that question. We are given that the work done is equal to 5 kilojoules and we're asked to find the heat transmitted, Q, unknown. We are given specific heat at constant pressure and volume, gamma, was given to us to be 1.66, and we're asked to find the heat transmitted and then the amount of heat that was used, how much of this heat is used to raise the internal energy. So basically we're asked to find the internal energy, U, unknown. Okay, so first thing, for a reversible
Isobaric process.
the very first thing that should come to your mind is to pull out your non-flow energy equation. Q is equal to U plus W. Okay, and similarly, or this simply implies that dQ is going to be equal to du plus dW. So this should always be your basic equation, and that should come to your mind first. Now, U itself, du, we've said this already, is going to be CV dt. We've said this in all our videos. Du is going to be CV dt, and dq, please keep in mind that for a constant pressure process, remember the question says at constant pressure, so pressure is constant, not forgetting pressure is constant. So this simply implies that my P1 equals my P2, that could be likened to be P. So at constant pressure, heat supplied dq is equal to Cp dt. Also keep this in mind, at constant pressure the heat supply is given simply as Cp dt. Now our work done, remember our work done is equal to P dV, and we know the equation of state PV equals to RT. Therefore P dV is going to be equal to R dt. Remember T, the arrow becomes 0 because the R is a constant. So P dV becomes R dt. So this simply means that our work done is going to be equal to R dt. Now this is what we are going to do. We know our heat. This is our heat equation. We know our work equation. Simply you can just call this Q to avoid ambiguity. Now let's find the ratio of heat and work. Q over W is now going to be equal to Q is Cp dt all over W is W is R dt. So from here dt cancels out. This implies that Q over W is equal to Cp all over R. So we can make our heat subject of formula here to get the equation to use to find the heat. Okay, so this simply implies that heat is now equal to, it becomes work done multiplied by Cp all over R. So this is our heat equation. We know the value of work done, but we don't know what Cp is and we don't know what R is. We need to now find Cp and R. Now you recall that the isentropic index of expansion and compression is given as Cp all over Cv, and we have the value to be 1.66. So from here we can simply make Cp the subject of the formula. That becomes 1.66 times Cv, okay, because gamma is 1.66 from here. So if we make Cp, it becomes gamma times Cv. Gamma is 1.66 times Cv. So this is now Cp 1.66 times Cv. So you can outrightly plug that into this equation if you wish. Let's call this equation star. let's call this equation star. Now you recall again that Cp, we said this in our previous video, Cp is equal to Cv plus R. Okay, the specific heat at constant pressure is equal to the sum of the specific heat at constant volume plus the gas constant. So if you have this, we know the value of Cp. We found out that Cp is 1.66 Cv. So we can relate the two of them from here. In place of Cp, you have 1.66 Cv equal to Cv plus R. So we can now make R subject of the formula. We have 1.66 Cv minus Cv. So this simply implies that our gas constant R equals this is going to be 0.66 Cv. So now we have our gas constant. Okay, so from here, if we have R, we have Cp, we simply plug into this equation to find the value of our heat. So if we do this, this is going to be equal to work is given as 5 kilojoules multiplied by Cp. The value of Cp is 1.66 Cv. So you have 1.66 Cv all over R, and R itself is 0.66 Cv. So you have 0.66 Cv. Cv cancels Cv. This means that the heat supplied equals 5 times 1.66 divides 0.66. So let's see what this value gives to us. 5 multiplies 1.66 divided by 0.66. So this simply gives us 12.58 approximately kilojoules of heat. So the heat transmitted is actually 12.58 kilojoules of heat was transmitted to the system. It's as simple as this. Okay. Now, having found the heat, the next question says we should find the amount of this heat that can be transferred. Right? Let me check the question again. So the next question says we should find the amount of heat that is used to raise the internal energy of the gas. So basically we have to find the internal energy. So you fall back now to the basic equation, which is the non-free energy equation, which is Q equals U plus work done, right? So let's fall back to that equation. I think we can do that here. So if we make internal energy subject, U is going to be equal to Q minus W. Okay, we know what W is. So U is equal to, we know what Q is. Q is 12.58 minus W is 5. So this simply implies that the internal energy is going to be equal to, I think that's about 7.58 kilojoules. Okay, so you have 7.58 kilojoules for the internal energy. So guys, that's how to apply the equation from the
Isobaric process.
to solve problems. I will see you in the next video. Thank you.